Test of independence is an application of chi-square distribution. Chi-square distribution have several other uses, out of which the one of them is test the equality of one population variance It can be used for testing of equality, testing the association or the independence to qualitative factors. And the third application of chi-square distribution was the test of goodness of fit. We can test whether a specific probability model can be used for a given data set or not. And the fourth application of chi-square test is testing the equality several population proportions. Okay, we are going to start describing the test of independence in this recorded lecture. According to the test of independence, we need two variables. One variable is a qualitative variable or a nominal variable x. Another variable is y, is also a nominal variable. So both variables are the nominal variable. And we want to check whether the two variables are associated or independent. Suppose we can say that the x is a variable which is describing by the grades of student. In a class. And another variable y I am assuming as gender, male, female. H naught is what? H naught will be the grades are unbiased with respect to the gender. Grades are unbiased or not associated with the gender. Unbiased with respect to the gender. And H1 will have the grades depend on gender. Grades, suppose grades depend on gender. Suppose the females are claiming that the boys got the higher marks as compared to the female, or the males are complaining that the teacher gave higher marks to the girls student, or vice versa. This can be done with the help of the chi-square test of independence. There are several applications of chi-square independence that can be applied on any field. There is only one restriction, and that restriction is we need the two qualitative variable. If your variable is quantitative, then you have to classify your quantitative variable into the groups or into the factors. Then after converting the quantitative variable into the group or into the factor, we can apply test of independence on that. We are considering one example from the class of Professor Neil Levis. In the class of Professor Neil Levis, he collected the data from his student about the political party affiliation of the student and the class level. So we have the two variable. One is the political party affiliation of the student and the level of the class in which the student is studying. Suppose the students are freshmen or sophomore, senior, junior. These are the four levels of class, and party affiliation has three levels here: Democratic Party, Republican Party, and other parties. Because small parties are collected in the another category, that category is assumed as a other. So the variable political party has three level and the class level has four levels, and the data is represented on the next slide. This is the data, and the data indicates that the first candidate or the first student support Democratic and his freshman. Other second student is a supporter of any other party, not Republican, not Democrat, and belongs to the junior. There are 40 students in the class of Nilevis, and this data is to be analyzed. So firstly, we have to make a frequency table, bivariate frequency table of this categorical data, considering the party affiliation on rows and class level on column or vice versa. So here the party affiliation is taken on the rows and class levels are considered on the columns. These frequencies, these tallies are recorded according to the data, and then the numbers are computed. This table is known as bivariate frequency table of two qualitative factors. We can also use a term for this as contingency table. Contingency table or bivariate frequency table of two qualitative factors. This bivariate frequency table contains the frequencies. What frequencies are there? The frequencies are, these frequencies are known as observed frequency. This is O11, row number 1, column number 1. This is row number 1, column number 2, and so on. So these frequencies are represented by OIJ. This is not the OIA, this is the total basically. The last frequency here is row number 3, column number 4. O34 is the last frequency here. So these frequencies are represented by OI. OIJ indicates what? OIJ indicates that observed frequency in ith row and jth column. I observed frequency in ith row and jth column. We have to calculate the some other frequencies. So initially we calculate the total of rows and the total of column. So this is the total of first column, second column, last column. This is known as a grand total. The grand total is represented by N and the row totals are represented by R or the Ri, total of ith row. And the column totals are represented by Cj, the total of jth column. So Ri, Cj, these are the two representation that we generally use for the row total and the column total. And how the expected frequencies are computed? As we have 12 observed frequencies, against these 12 observed frequencies, we have to calculate 12 expected frequencies. The formula for computing the expected frequency is E is equal to R into C divided by N. Or in general, I can write down it as EIJ, expected frequency in ith row and jth column, can be computed by total of ith row is represented by Ri, total of jth column Cj divided by the grand total. So for simplicity, you can represent the formula of expected frequency by R multiplied by C divided by N. This is the way of computing the expected frequencies. After computing the expected frequencies, we have to consider the chi-square observed statistics. That can be done by taking the difference between the observed frequency and the expected frequency, whole square of that difference divided by the expected frequency. The formula is represented here. Observed frequency minus expected frequency whole square divided by the expected frequency. And the summation is on all over there. Summation is not only on numerator, it is on the ratio. This is the formula of chi-square test of independence, and degrees of freedom of this formula is R minus 1 times C minus 1. R minus 1 stands for the number of rows minus 1, number of columns minus 1. If I am implementing it to the class of Nilevis, so in the class of Nilevis, I have 3 rows because 3 parties are there. So 3 minus 1 multiply by 4 columns were there, 4 minus 1. So 3 minus 1 times 4 minus 1 is the degree of freedom for our contingency table of 4 by 3. After computing the 4 by degrees of freedom, we can have the value of critical number. The null hypothesis, this is the procedure. In this procedure, the two variables are not associated. That is the null hypothesis. Do not take the association between the two variable in the null hypothesis. It is always not associated. And in the alternate hypothesis, two variables are associated. Alpha is to be decided. Then computing the formula of chi-square statistics by O minus E whole square divided by E. And then critical region or the p-value approach. Any approach can be used for testing the hypothesis. There are the 3 assumptions which are major assumptions in the chi-square distribution. So all of the expected frequencies are 1 or greater than 1. If some of your expected frequencies are less than 1, means the assumption is not fulfilled. At most 20% of the expected frequencies are less than 5. So you can apply this condition. If there are more than 20% of the expected frequencies are less than 5, so we have to merge either column or rows to reduce the size of the contingency table and recalculate the chi-square statistics on the data after fulfilling the second assumption. The third assumption is indicated that simple random sample means the data must be random. If the data is not random, we cannot apply the chi-square test of independence. So these are the assumptions. The assumption must be fulfilled before implementing chi-square test of independence. Critical number is here. You can see the critical number. This critical number is obtained by chi-square alpha, not alpha by 2, because we always use the right tail test in chi-square distribution. Chi-square alpha with the degrees of freedom nu. This number is obtained from the chi-square table. This point is referred to as critical point. If the observed value of chi-square statistics, this is the observed value of chi-square statistics. If this observed value of chi-square statistics is larger than the critical number, then the null hypothesis is rejected. And if the observed value of chi-square statistics is smaller than the critical number, the null hypothesis is accepted. So null hypothesis, if the null hypothesis is accepted, meaning that the two factors are independent. That's all for the procedure. Then we have to implement this into one complete example. In this example, we have the two qualitative variable. One of them is the marital status, other of them is the drinking habit. Drinking habit has 3 levels: abstain, 1 to 60, and over 60. It is categorized. It is not considered as a quantitative variable. It is a categorical variable because it is bifurcated among the three factors. And the marital status, the pure nominal variable, the marital status have four levels: single, married, widowed, divorce. What to do? We have to check whether there is an association between the marital status and the drinking habit or not. So the null hypothesis will be what? The two factors are independent. And the alternate hypothesis is what? Marital status is associated with smoking habit. So this can be done with the help of chi-square test of independence, the null hypothesis, marital status, and the alcohol consumptions are not associated. The alternate hypothesis that the marital status and alcohol are associated. Meaning what? Meaning that either the participant started drinking after marriage or due to the marriage, or vice versa. Meaning that someone is taking alcohol because he or she is not married. So the cause cannot be determined with the help of chi-square test, but we can check only whether the association or not association. Now the calculations are to be performed. Expected frequencies can be computed with the help of the row total multiplied by the column total divided by the grand total. This is the formula of computing the expected frequencies. The 12 expected frequencies are to be computed. The first one is represented here. 590 divided by 1772 multiply by 1173. That is the first expected frequency. This is represented by the first expected frequency, E. Now, in the same way, we have to calculate all the expected frequencies, row total multiply by column total divided by the grand total. The formula is again represented here. All these frequencies are computed and summarized in the table. First observed frequency, it is 011 is 67. I can represent it as 011 means observed frequency in cell number 1, column number 1. It is 67. Against 011, I have an expected frequency E11. It is equal to 117.9. How 117.9 is computed? Quite simple. 354 is multiplied by 590 divided by 1772. This ratio is 117.9. In the same way, we have to calculate the all expected frequencies, 191.2, 44.9, and the last expected frequency is 13. Now we have to calculate the chi-square values for each cell and check the assumptions. All expected frequencies are greater than 1. None of them is smaller than 1. The assumption number 1 is fulfilled. All expected frequencies are greater than 5. None of them is smaller than 5. The second assumption is fulfilled because we have an allowance of 20%, but here we have 100% expected frequencies more than 5. The third one is the data is selected randomly. All the three assumptions are fulfilled. We have to calculate the first value of chi-square statistics is 67 minus 11, 117.9 whole square divided by expected one, 117.9. This number is the first value of chi-square statistics. In the same way, you have to calculate 12 values of chi-square statistics, and then total of all of these chi-square values is to be find out. This total is represented here. The first observed frequency 67 minus first expected frequency 117.9 whole square divided by 117.9 and so on. This is to be added 12 times. So you can see here are the plus signs. How many plus signs we have? 11 plus signs we have because 12 terms are to be added. The total is 94.269. This is the value of chi-square observed, or the chi-square statistics. This is the value of chi-square observed value of chi-square statistics. Now we can apply the procedure, null hypothesis, alternate hypothesis, all the expected observed frequencies, marital status and the alcohol consumption are not associated, null alternate hypothesis. The value of alpha is 0.05. The formula is chi-square O of minus E whole square divided by E, and the sum of that. And again, I am representing the sum is on all over there, not only on denominator. The calculated value is 94.26. This is known as chi-square observed value. Chi-square observed value is 94.26, and we want to find out the critical point. Critical number is to be obtained with the degrees of freedom r minus 1, c minus 1. Total number of rows were 4. So 4 minus 1 multiplied by 3 minus 1. This is the degree of freedom. 3 minus 1 is 2. And 4 minus 1, it is 3. So 6 degrees of freedom we have. So chi-square value at 0.05, 6 degrees of freedom, it is 12.59. Always use right tail test with the complete alpha on the right side. So do not use alpha by 2 here. Alpha is to be used in a chi-square test of independence, and in a chi-square test of goodness of fit, we always use right tail test. The chi-square critical point is 12.59, and the critical interval is 12.59 comma infinity, with the round bracket here and the square bracket here, meaning that this is the rejection region. If the chi-square observed value falls within the critical interval, then we reject the null hypothesis. My value of chi-square observed is 94.26. So clearly it is falling in the rejection region, and it is greater than 12.59. So we have to reject the null hypothesis. Data provides sufficient evidence in favor of H1, and conclude that marital status and alcohol consumption are associated. But we cannot say anything about whether the alcohol consumption depend on the marital status or marital status depend on the consumption. So we cannot cause any factor to the other factor, but we can say that there is a significant association among these two. So in the chi-square test of independence, we have two qualitative variables. The association between the two qualitative variables is checked with the help of chi-square test of independence. Suppose we have two quantitative variables. How can we check the association between the two quantitative variables? The association between the two quantitative variables can be checked with the help of correlation. So we have another test, rho is equal to 0. Rho is equal to 0 means what? The two quantitative variables are not associated. So as the same null hypothesis we have here in the testing of correlation, but in testing of correlation, we should have to summarize the two quantitative factor. Rho is equal to 0 means correlation is equal to 0. So if we want to check the association between the two qualitative variable, we can check it with the help of chi-square test of independence. And if you want to check whether the two quantitative variables are associated or not, we can test the value of the correlation, whether it is 0 or not. Two more questions are given here in this presentation. One of them is education level and the diabetic state. Whether diabetes depends on education or not. The null hypothesis is what? Education and the diabetes state are independent, and diabetic state depends on education, or they are associated. In the alternate hypothesis we can have. So you have to apply the chi-square test of independence to complete this problem. And we have another problem here, that is BMD, bone mineral density, and depression, whether the bone mineral density of participant is independent of depression or not, or the depression depends on the BMD or not. So another hypothesis will be what? The two qualitative factors are not associated with the alternate hypothesis that the depression and the bone mineral density are associated. Either depression is due to the bone mineral density, or due to the depression there is an impact on bone mineral density. So we cannot analyze the causation with the help of this test of independence, but we can check whether they are associated or not. Thank you very much for this lecture, and inshallah in the next lecture we will record a complete application of chi-square test of independence with the help of SPSS.